Last day of the semester for Mastering Chem, but I guess for Chapter 24 I didn't. Unfortunately, I'm locked out of my Mastering Chem account. I called tech support and they're supposed to do something. I called them at the beginning of the week, but still I'm locked out. It's asking me to pay to access my course. Although I don't want to pay for it, so I'm still trying to work it out. But just submit it next week is fine. So don't worry about the due date. Okay, it's going to mark it as late, but when I eventually get back into Mastering Chem, I could reset the due date, and then it should correct your score. All right.
I mean, since I missed a little bit of the class on the first day, is the homework that we need to do that on Pearson?
Yeah.
Okay.
It's Mastering Chemistry, Pearson. There's a link to my course, and it's going to take you. If you have it from last semester, you can just enter it. Your code should be good for a year, 12 months, so you should be able to enter it in there.
I may have missed it, but did you talk about the lab manual for this semester?
Yeah, briefly. The lab manual is, there is no lab manual at the bookstore. What you're going to do is, I'm going to put the labs on Canvas, and then you can just download them onto your device or print them out.
All the chapter exams might be multiple choice or multiple choice.
The chapter exams are typically like one page, multiple choice, like 2/3 or something, and then some free response, a couple of free response questions. The chapter exams are relatively short. It's not going to be like a 5-page exam or something like that on it. Some people say they're more like quizzes, chapter quizzes rather than exams. But they're worth 50 points, so it's significant. Okay, other questions? All right, then we're going to continue with Chapter 24. Let's see. Chem native. Nomenclature. So I have to record this on the iPhone still. Hopefully I can get the other thing fixed. I'm going to just reload the program over the weekend. Oh, this is just working a minute ago. Indicator. Okay, there it goes. All right, so we talked about the ligands, correct? These are what we call monodentate ligands. You can see some common monodentate ligands. Monodentate means only one lone pair, binds. And if only one lone pair binds, then only one donor atom. I call it a donor atom here. So when we're looking at this, did we talk about nitrogen trifluoride?
Yep.
Yeah, what would be the donor atom here? This is not a very good donor atom, because we want kind of negative charge density on the nitrogen. So this isn't going to be as good as ammonia, which is here. Nitrogen trifluoride, when we look at the oxidation state. Did I talk about this already? Yeah, it's +3. But nonetheless, we'd expect nitrogen to be the better donor, even though fluorine would have the -1 oxidation state, and you'd expect, okay, that's gonna be more electron rich, that should be a donor. Fluorine never wants to donate. Why is that?
It's the most electronegative.
It's the most electronegative atom, and number 2, if it donates, then it changes its formal charge, it become less, but it doesn't. And so still here, even though this is a +3, +3 is not great, it's more, what we say, blue. Blue is for acids, yeah, and this is supposed to be Lewis bases, so this is more acid-like than base-like. And this would be more red. So this is an excellent donor here. This wouldn't be as good of a donor, so I'd expect this one to be much better. And this is what we call a mean. This is not a mean here, and then we have the means there. Those are the monodentates, and then we have the bidentates here. We talked about this, right? Ethylene diamine, correct? And the others. So I want to go into nomenclature, and this morning I wasn't able to get into the book, but now I think I was able to get into the book. I still can't get into mastering chemistry. This is what I get when I try to go to my course. It says I get this, register, but somehow I was able to open the book. And so I want to go, oops. And this is weird because normally when I sign into Mastering Chem, I can, like here, when I sign into Mastering Chem, my course has disappeared. Welcome to Mastering Chem, create a course. But what happened to my course? It's gone. And so the tech person I spoke to couldn't figure it out, and so it got escalated, but I still haven't heard back from them. But hopefully my course is still there. I think it's still there because somebody asked me a homework question.
It's still there.
It's still there? Okay, that's good. Okay. So let's talk a little bit about ligands and some other stuff here. So when we have these complexes are formed from what type of reaction? Metathesis, acid-base, or redox? Acid-base. And as far as acid-base goes, all acid-base reactions are Lewis, but a subset of them are Bronsted. Could we call this a Bronsted acid-base? No, these are all Lewis acid bases, and the Lewis acid is the metal. We call it the central metal. That's our acid. And the metal has no proton to donate, no hydrogens, so this would be our Lewis acid. And the ligand is going to be an electron pair donor. So we'll just write L for ligand, and we'll put an electron pair that it can donate. And so this is our Lewis base. So this is our Lewis acid and base. Now the ligand can be neutral. That would be a 0 charge, like ammonia. Or it could have a charge, like chloride. And so we'll just say minus Y. Charge. And then in Lewis acid-base reactions, the base always attacks the acid. So this lone pair here attacks the acid, this. And what forms here? A bond forms. What type of bond? What do we call this bond that forms here? A covalent bond. Normally, when we think of a metal and a non-metal, I don't think covalent bonds. When I have a metal and non-metal, I automatically think it's an ionic bond. But here it's kind of weird because now we have a metal and a non-metal. It's going to form a covalent bond. And the bonding on this, is best described using what theory? Molecular orbital theory. It's not very successfully described using the other theory. What was the other bonding theory? Valence bond theory. Valence bond theory was not enough. One of the things I don't like about the book is the book writes this. They'll show the bond, and we call that bond, what do we call this bond again? What type of bond is that? It's a covalent bond, but it's a special covalent bond. Because in a normal covalent bond, one dot comes from this and one dot comes from that, and they share the two dots. In other words, one electron comes from atom B, another electron comes from atom A, and then we form the AB bond, right? But this is a special one where both bonding electrons come from the ligand. Both bonding electrons come from the ligand, then we give the covalent bond a special name. What do we call the covalent bond?
Bond polarity.
I'm sorry?
Bond polarity.
Bond polarity can be for any bond, ionic or covalent, doesn't matter. Bond polarity is just how polarized the electron cloud is. Polarized means pulled in one direction or the other. Coordinate covalent bond. What's another name for a coordinate covalent bond? Dative bond. And so what we're going to form here is a coordinate covalent bond or a dative bond. Here. It's not such a big deal because you can't tell the difference between a coordinate covalent and a regular covalent bond, once it forms. It's just like any other covalent bond. Right? And it's just a way of bookkeeping things, that's all. And so some people want to know that. But one of the things I don't like about our book is our book will write the coordinate covalent bond and then they'll show a lone pair stuck in here. And so what's going on with that? I don't like this when the book shows the lone pair in here, stuck in here. Because now it looks like there are 4 electrons, right? 2 from the bond plus 2 from the lone pair, that's 4 electrons. Where did the 4 electrons come from? Because I didn't start off with 4 electrons, I started off with 2 electrons, right? And so, our book does it, but other books do it, but some books don't. And I prefer the books that don't, but Petrucci there's some things I don't like about Petrucci, but overall it's a pretty good book, so I'll live with this here. Otherwise, I'd ask for using a different book. And so now the ligand is essentially giving up one of its electrons. But here, when we count the electrons, both electrons belong to the ligand. Over here, now, if we do this using, what were the 2 ways of counting electrons in a bond? We could use,
Double count them.
we could use formal charge, or we could use oxidation state. So when we count the electrons in the bond, we either split them, or we give them to the more electronegative. Right? And so in this case, if we're to split it, then 1 electron goes to the metal, 1 electron goes to the ligand. That's what we normally do, formal charge. So that's going to change the charges here. So originally the metal was plus X. Now it's going to be plus X minus 1. It's going to be plus X minus 1 because it's got 1 more negative charge, right? And the ligand was 0 or minus Y. Well, if it loses 1 electron, then it's going to become more positive. And so that's going to change it to plus 1 or 0, right? Or plus 1 or not 0, but minus Y plus 1. Is that right? Yeah, minus Y plus 1. But are we gonna do that in complexes? Do we count electrons normally, like we do everything else in complex? For the ligand itself, no problem. You know, both those electrons belong to the ligand, but in complexes, we don't count the electrons like we normally do. And so what we do is we leave everything as it was. So the metal started off as plus X, and when we form the complex, the metal is gonna end up at what charge? What's the charge on the metal in the complex?
0.
Plus X. So it's kind of weird. You know, it doesn't make sense, but it doesn't have to make sense because we're using valence bond theory to describe the bonding in metals. You know, and not only that, I think it's more bookkeeping. This is to make your life easier for keeping track of charges and electrons. You know, it's just much easier to do it this way. So we're not even going to bother changing the charge. Everything's going to stay the same as it was before. So as the free species, these are called the free versus the complex, we use the same charge. And so this is or minus Y. Even though for sure we would expect it to change there. We don't track it. All right, and so this is going to form a complex, or in general, it's something we call an adduct. A complex is for metal, but an adduct is for anything. You know, this Lewis acid is what we call the central metal or the metal ion here, or metal, central metal atom. An adduct can be whatever we use for the acid. This is you know, we're just looking at parts of the acid-base universe, and the part of the acid-base universe we're looking at here are the complexes, the transition metal complexes. And so I'm going to abbreviate this TM for transition metal, because the transition metals make decent Lewis acids. Some other metals also make decent Lewis acids, like aluminum. Well, aluminum is not a transition metal, but it's a pretty good Lewis acid. However, the group 1, you know, the alkali metals, and even the group 2, the alkaline earths, aren't very good. Size and charge is one factor, plus the bonding is another factor. So it's primarily focused on the transition metals and aluminum. But other metals can form complexes. You know, they're just not very strong. And so we'll look at those a little bit. All right, so let's see. I wanted to talk about this. Let me see. This would be an example of a monodentate ligand. A monodentate ligand just bites in one place. And so here, the ligand, what do you say, binds, let's say monodentate. Monodentate. A monodentate ligand just has one donor atom. And we can see some examples of monodentate ligands. I'll give you one that's not very good. Oxygen. Except, you know, oxygen, how do I want to represent oxygen? You know, if you had me for Chem 1A, I tried to represent oxygen using molecular orbital theory. I don't know if anybody remembers that, but I tried to draw out the sigma 1s and then with one color and then the sigma star 1s. Maybe I skipped the core. I did the sigma 2s followed by the sigma star 2s followed by the sigma 2p and the pi 2p's. Does anybody remember that? That turned into a big mess. And so what we're gonna do is, I know this is not correct, but I'm just gonna draw the Lewis structure of oxygen like this. Why is this not correct?
Comes out as diamagnetic.
Yeah, this shows oxygen is diamagnetic. Everything's paired up, right? But oxygen in reality is not diamagnetic. But oxygen can be a donor. Now we got to figure out, well, where are the pair of electrons coming from? What orbital are the pair of electrons coming from, right? But anyway, this is going to be easier for us. So one donor atom that can bind. And so here, we'll pick a metal like iron. Iron 2 is a transition metal, and iron 2 comes in what charges? 2 and 3. I'm gonna use iron 2 plus, because in blood we have iron 2 plus. And then this is actually kind of big. There's a whole bunch of other stuff here. And these are rings, it's flat. I'm making them jagged, it's not really jagged. This is called the heme, like in hemoglobin. And so what we have is, we have iron 2 plus, our acid, and oxygen is our base. And what can happen here is we're going to get a Lewis acid-base reaction. So the base attacks the acid here and binds. So the iron 2 plus, or bonds. So what do we do to the charge when we form this bond to the oxygen? Should I change the charge on the iron 2 plus? No, I'm not going to change the charge on iron 2 plus. And oxygen likes to form 2 bonds. Like one double bond counts as 2 because we got a sigma bond in there, and we have a pi bond, right? When oxygen forms 3 bonds, in this case we have 2 sigma bonds and 1 pi bond, so that's 3 bonds. It typically does not have a 0 charge, right? When oxygen forms 3 bonds, like in hydronium, it forms what charge? A plus charge, So oxygen likes to form 2, but it can form 1 bond, it can form 3 bonds, Well, typically if oxygen only forms 1 bond, we end up with 3 lone pairs to complete the octet, and we end up with a negative charge. 3 bonds in oxygen ends up with a positive charge. Here, are we going to change the charge on oxygen? No, we're going to call oxygen 0 charge, neutral, even though it has 3 bonds, which you wouldn't do in normal. So we just do this for complexes, since we ignore all the counting rules in complexes. But what kind of bond is that? That would be a coordinate covalent bond. But the situation with coordinate covalent bonds is they aren't all strong. When we think of covalent bonds, we think of things that are pretty strong. Even the weak covalent bonds, some of the weaker covalent bonds, like the peroxide bond or the iodine bond, it's pretty weak, but still it's substantial. This is really quite weak. And so in some cases, I'd like to call that a coordinate covalent bond, but in this case, I just like to think that oxygen binds to it, not really bonds to it.
Is it weak for the sake of it being able to be taken off
Yes.
easily by cells?
Right. Because if this were strongly bonded, you would die, right? Because the purpose of the hemoglobin, the purpose of this is to transport oxygen. And so it has to attach and be loosely held so that it can break off. Otherwise, we can't. Because there could be a problem like this, So to contrast that, let's pick something that's a much better electron pair donor. Something that's a much better electron pair donor, one of them that I can think of is carbon monoxide. Carbon monoxide is an excellent electron pair donor. And so let's say I had a competition between oxygen versus carbon monoxide. Who wins? So when I look at carbon monoxide, there are two lone pairs. One lone pair on oxygen, one lone pair on carbon. And then here we got 4 lone pairs, so any one of these will do. These are all going to be monodentate because we're not going to donate more than one. I mean, if this is sp2, which we wouldn't use valence bond, but I'm going to use valence bond here. This would be sp2 lone pair. This would be sp2 lone pair. We are going to have an sp2 sigma bond and a pp pi bond, right? And so when we're looking at this, which of these 2 lone pairs will we do? We can't do both of them, because the orbitals, this is sp orbital, this is sp orbital, they're on opposite ends, so 180 apart from each other. And so which would be the donor? Would it be a carbon donor or an oxygen donor? So this is going to be monodentate, that is only one of these atoms can donate. Which one is it going to be? Carbon or oxygen? Which would be a better donor? Carbon. For sure, carbon's going to be the better donor. Why? Why is carbon going to be a much better donor than oxygen?
Isn't it like if you count things, it's carbon has the negative and then oxygen has the positive?
Yes. Okay, I said ignore the formal charges for complexes, but we can't ignore the formal charges for the ligands, The ligands are just regular molecules. And so when we do the formal charge here, carbon ends up with an extra electron. It has 1, 2, and then half of these bonding electrons. It would be 3, 4, 5. 5 electrons. Carbon's only supposed to have 4, so it comes up ahead. Oxygen has 1, 2, and then 3, 4, 5. It's supposed to have 6, so it's 1 short. So based on this, the better base donor, the better donor is going to have negative charge density plus a lone pair. And so this is why I asked you up here. Oops. Here we have 2 nitrogens, but the 2 nitrogens aren't the same. Do you see that? Both nitrogens have a lone pair, but one of these nitrogens is clearly going to be a better donor. Which one is it? Ammonia. Ammonia is going to be a much better donor than nitrogen trifluoride. In fact, let me do a little side topic here regarding formulas, writing formulas. We'll talk about it here. Ammonia has another name. What's the systematic name for ammonia? That's a binary molecular compound. So I go back to chapter 3 and look at the nomenclature rules for binary molecular compounds, and how would you name it? Like water, What's another name for water? Dihydrogen monoxide. Well, what's another name for ammonia? Nitrogen trihydride. I don't like this name. Do you know why I don't like this name? I don't like this name because do you know what hydride is? Hydride is, it's the anion form of H, which is H minus. So if we have 3 hydrides there, trihydride, that's 3 negative charges, which is -3, which makes nitrogen plus 3. Nitrogen plus 3 is wrong, right? It's not nitrogen plus 3. So I don't like this name. Rather, I think ammonia should be written this way, H3N. But the reason they don't write it is they might get confused with acids here. But let's name this. How would you name this? Yeah, trihydrogen. Nitride. Nitride is nitrogen with what charge? Like fluoride, oxide, nitride. Fluoride's -1, oxide's -2, nitride is -3. That makes sense to me. So this gets the electron density correct. But nobody ever writes it like this. Well, when I was looking in books, you know, not books, but catalogs, chemical catalogs. Yeah, I might have mentioned this in Chem 1A. I couldn't find ammonia. I was thinking, why? Ammonia is such a common chemical. Why don't? This is a European chemical company, and then I figured it out. They didn't call it ammonia. You know what they called it?
Trihydrogen.
They called it nitrogen trihydride, and so I ordered some nitrogen trihydride. But I think that name. So what would be more appropriate here? What would be more appropriate for NF3? Should we do this? Should we call it nitrogen trifluoride? Or should we call it trifluorine nitride? What would be more appropriate for NF3? Nitrogen trifluoride. You know, fluorine's going to take the electrons. Here. Fluorine's more electronegative, takes electrons. So nitrogen trifluoride makes perfect sense here. It doesn't quite make sense here. Whenever I hear nitrogen trihydride, I think that's backwards. That's backwards because hydrogen doesn't take the electrons from nitrogen. You know, normally we write the positive species first, followed by the negative species. If we were to do that, then hydrogen should be the positive species and nitrogen should be the negative species here. I'll come back to this in a minute, but anyway, this is going to be quite red. You know, that always confuses me too. So I always have to go back and think about it because I always think base is blue, and so I have to think bases are red, and so that's why I don't like the electrostatic, and that's why I complain about it so much. But anyway, this is native. Maybe I'm not going to go into the color scheme. This is just native. We're looking at this is going to be a much better donor than this. But compare these two, which one would be better, oxygen or carbon monoxide? Carbon monoxide. So what happens here is carbon monoxide forms a strong coordinate covalent bond here. In fact, it forms too strong of a bond that it doesn't break off, or it's very difficult to break off. And yeah, and so what I like to say is that, you know, one donor atom that binds, you know, let's say, these are all monodentate ligands here. And in this case, if the carbon binds here, the oxygen is on the opposite end, it's not going to bind. You know, it's too far away. And so these are monodentate, even though they have multiple lone pairs that can bind, but they aren't going to bind because of the direction. If this is sp, so it's linear. If this were sp2, then we have this sp2 orbital here, and this sp2 orbital would be pointed this way. So maybe in theory we could, but we're going to get poor. If we're thinking valence bond, which we shouldn't be thinking valence bond, then it would be very poor orbital overlap. You know, it just doesn't quite fit to bind this oxygen here.
Are all linear structures monodentates?
Are all linear structures monodentate? Yeah. I'd have to think about that. Maybe there's an exception there. You know, if it's diatomic, it's going to be monodentate. And so all linear, you know, all diatomic species are linear. So all diatomic species are going to be monodentate. But when we get to triatomic, if we have something that's linear, that's triatomic, or, you know, what's after tri? Tetra, you know, or penta, then maybe there's a chance it could be bidentate. In fact, let's look at polydentate ligands next. So, yes, this is a coordinate covalent bond, but sometimes I'm going to just say that the ligand binds rather than bonds to it, because, you know, the bonds can be extremely weak like this, or they can be exceptionally strong like this here. And what's going to dictate the strength of the bond is usually what we call HSAB. Does anybody recall the acronym HSAB?
Hard, soft, acid, base.
Hard, soft, acid, base. So we'd have to approach this more quantum mechanically, and then we can better understand the strength, bond strengths based on that. But usually it's simple. If you have good, orbital overlap, like in valence bond theory, then you're going to have good linear combinations of atomic orbitals in MO theory. So probably the most common polydentate ligand. So polydentate is more than one donor atom. The donor atom is going to give up its lone pair for the bond. So the typical polydentate ranges from 2 to 6 donor atoms. So if we're dealing with 2, we call it bidentate. If we have 6 donors, it's called hexadentate. And so now we're going to look at a couple of common bidentate ligands. The first common bidentate ligand is called ethylene diamine. So ethylene diamine. It's all one word. Now, when I spell diamine, should I use 2 M's or 1 M? I only use 2 M's when I'm dealing with what? Ammonia. Ammonia is a monodentate ligand. This is bidentate. I got to use 1 M here. So diamine with 1 M. Ethylene diamine. So, do you guys remember what amine? Yeah, it's ammonia analog or derivative or just ammonia-like species. Do you know what ethylene is?
2 carbons.
Yeah, 2 carbons, that's good. It's a 2-carbon chain. Ethylene has is a CH2-CH2 chain. And so this part of this is a 2-carbon chain, CH2-CH2. There's a molecule called ethylene in organic chemistry. The ethylene molecule has a double bond here, but in this case, we don't have a double bond here. We only have a single bond. And so this is ethene or ethylene. And so it's not this that we're looking at here, but it's a 2-carbon chain. And then it needs 2 more things attached to it, because carbon needs 4 bonds. So we have this CH2, we have 2 hydrogens here, and the carbon's bonded to the carbon here, so we have 1 more bond here, this is a dangling bond. But that's where we're going to throw in amine. Amine would be ammonia, but in this case, ammonia has 3 hydrogens. What we're going to do is we're going to remove one of the hydrogens and bond it to the carbon, and so that means we're going to be left over with 2 hydrogens. Actually, I'm going to draw this condensed, and then I'll draw it expanded next. And so this is it. We're going to throw the amine NH2 group out here, and then we'll have an NH2 group here. So ethylene is going to be NH2, CH2, CH2, NH2. That's ethylene diamine. Now, you should, we'll do another little side topic here. You should review the organic prefixes or parent chain, like meth. F. What's after F? Prop. After prop, but, and then pent, hex, not sept, hept, with an H. Oct, non, or known,
Deck.
deck. So these represent what?
How many carbons?
How many carbons? Chain, in the longest chain. There's 2 carbons, so F. So this is ethylene. Methylene would be 1 CH2 group. Propylene would be 3 CH2s in a chain, etc. So this is ethylene diamine. Organic chemists usually don't show the lone pairs. I'm going to show the lone pairs here. Lone pair here. Oops. Let's do black. And a lone pair here. All right. And so this is what we call a bidentate ligand. And we're going to react that with some cobalt. Now, cobalt, what are the 2 common charges for cobalt?
Plus 2 plus 3.
+2 +3. I'm going to use cobalt 3 plus here. Okay, and the ligand, this is bidentate ligand, ligands are going to attack the central metal, called this the central metal. So the ligand, the base, attacks the acid. Like this. Okay, so I'm going to redraw that here. So the lone pair on the nitrogen binds or bonds to the cobalt. Like something like this. What's the hybridization on this nitrogen here?
SP3.
sp3 carbon?
SP3.
Okay, so this bond is called a what type of bond? sp3 sigma bond in valence bond theory. And so if you look at the sp3 orbitals, they've got those lobes here. If I were to twist this like this, would it break the sp3 sigma bond overlap? Would it break the bond? No. And so we know that there's free rotation about single bonds. However, if this were a double bond, then double bonds don't have free rotation, because double bonds also have a pi bond, and the pi bonds are going to be like pp pi bond. So if you try to rotate one of the p orbitals, you're going to break the overlap, right? And so the orbital. And so there's no free rotation about double bonds, but there's free rotation about single bonds. So now this is monodentate. But what can happen is this is like a spaghetti noodle. This is all flapping around, and eventually what happens is the second nitrogen can attack the cobalt. Now, we don't do anything with the charge, so I'm just going to keep the charge of cobalt 3+, even though it's now bonded to this, and I'm going to keep the charge on nitrogen 0. I'm not going to add any formal charge to that. And then I'm going to have the second lone pair attack the cobalt here. It just flops around and eventually it can attack it once it's in the right proximity. And then it forms this. So, as you can tell, what happened to the lone pair? The lone pair was used to bond or bind to the cobalt. And the same thing here. So I'm not going to show an extra lone pair there because there is no lone pair there. I mean, if you put a lone pair there and 4 bonds, that would violate the octet rule. Nitrogen never violates the octet rule. And then we have it. So this is an sp3 sigma bond, but what about this bond here? Is that an sp3 D2? Or what is that? Or sp3, sp? No, we don't do that. We're not gonna hybridize this essential metal. I'm just gonna leave it like that. And we're not gonna describe the bond in that fashion. It doesn't work. Although some people will try to do that. Okay, so now, when we have a bidentate ligand, or whenever we have a polydentate ligand, it's special. It's special because it's so hard to break off. You know, if I try to remove this ligand, let's say I break this bond here. I break this bond and this thing flops around like a noodle. Okay, while this thing's flopping around like a noodle, I try to break this bond, but in the time that it takes me to break this bond, it flops around and reattaches. And so I break this end off. And then, okay, I go back to break this end off. And then it reattaches. And I break this end. They're very difficult to break off. Do you see why? Because the other end's flopping around, the other end can easily reattach. And so therefore we call polydentate ligands blank agents. Do you know what word we use? We call polydentate ligands blank agents. And so what is the blank here? I'll do it up here. Polydentate ligands are called chelating agents. And so what people visualize here is chelating is like the claw of a crab. And so it's like once the crab grips onto you, it's hard to break them off, I think, or get them off. And so that's what they're thinking here. Whereas monodentate is a lot easier to break off. You know. Some monodentates a lot easier than other monodentates. You know, it depends on the strength of the bond that's formed there. But in this particular case, it's chelating agent. And so bidentate ligands, you know, by their very nature, are very difficult to break off. But you know what? It looks like cobalt can be attacked, right? Again. Because if you're another ethylene diamine floating out here, you're going to see this cobalt, and this cobalt is going to be open on this side, and so it could be attacked again, right? But will it be attacked? Will it be attacked? Well, that depends on what we call the coordination number of cobalt. CN is called the coordination number. And that's equal to the number of donor atoms max for the metal cation, or metal, say metal center. It's kind of weird because it doesn't even have to be a cation. There are some complexes with a neutral metal atom in the center of it. So this is why I'm going to call it metal center rather than metal ion. And that metal center is going to act as a Lewis acid, even though when we think of metals being electron rich, you know, it's just the way these ligands combine to it. So if the coordination number of cobalt-3 is 2, we have to stop here. And then you go, why stop there? Because it seems to be more room, right? But how do we determine it? Well, what we need to understand is we need to understand the theory underlying this. But the problem is we're not at that stage in the. You know what stage? Maybe we're at a higher stage, but to get to that stage, we need some quantum mechanics. There isn't a simple law. If there was a simple law, it'd be great, you know. But we probably need some more quantum mechanics. So where we're at is kind of at the earlier stages. When we think about the scientific method starts off with what? Observation. So we're kind of like at the observation phase. You know, what's observed for cobalt-3? You know, what do we see? And so what's observed is we just look it up, and then maybe we're in the pattern, pattern stage. Is it goes observations and then what? Well, hypothesis is hard to get just from straight observations. You have to take lots of observations in order to get to the hypothesis stage. So what we do is we take those observations and then we try to do something called data reduction. Have you ever heard of data reduction? You have tons and tons of data, and what you try to do is you try to reduce it into simple patterns, right? And this is called data reduction. And so we'll have that, and then we'll try to reduce it into simple patterns, and then maybe generate some laws, and then we go to hypothesis from there, and hopefully to the theory. It'd be nice to be able to theoretically tell, have cobalt 3 plus what's a coordination number. And so the coordination number, we're at the point where we just look it up in a table. We have a pretty good table in our book. You know where the tables are located in our book? The tables in our book are located either in the chapter. The chapter is kind of the short version, but we have a longer version of the tables. They didn't put the long version of the table in the chapter because it'd take up too much space. So they're all located in the back of the book in appendix. You guys remember the appendix? Appendix D. D for what? D for? Well, maybe it was just A, B, C, D. Is there appendix A? Yeah, there's appendix A, B, C, D. But no, they made it trying to make it kind of crafty. D for data. No, so we're going to go to the appendix D, the data table. So let's take a look at the data tables here in appendix D. Fortunately, I don't know why they still gave me access to the book, which is good. I didn't have to pay for that yet. So we'll go to appendix A. Appendix A is math, appendix B is physics, appendix C is SI units, appendix D, data. And are they going to make me scroll through all the data tables? Shoot, yes. They are. All right, so D1, electron configurations. D2, what's thermodynamic data? We're going to have to go back to thermodynamic data. While I'm here, is there a thermodynamic standard temperature? Like STP? No. But since we do most of the reactions at room temperature, which is 25 degrees C, that would be 298 Kelvin or 298.15 Kelvin, depending on how precise you want, how many things you want. But there are, these are all, do you see this little zero here? Delta H naught, these are all under standard conditions. Standard conditions are 1 bar and, but it says roughly 1 molar because we need activity. It's actually activity of 1. Does anybody remember what activity is? Effective concentration. And if you wanted to review activity, where would you go? What chapter was that in? You're going to need activity for this Chem 1B. And so you should go and read it. It's like 2 pages in chapter 14, at the end of chapter 14. Just read it. There. Maybe I should show you here. Just do a search. I don't know what page this is. This is chapter 14. The other is an effective concentration called the activity, which takes into account the interionic attractions. So go back and read what activity is. So we have the stoichiometric concentration based on, this formula, the ratios, and the effective concentration is what they're talking about here. And so you should know the difference between stoichiometric concentration and activity. Actually, does anybody know? No? Okay. Let's go back to Appendix D. As long as you keep the concentrations low, then the effective concentration and the stoichiometric concentration are close. When the concentration gets high, then we start to deviate from ideal behavior quite a lot. And so we have ideal solutions and real solutions, just like we have ideal gases and real gases. But, activity and 1 molar is not too big of a deviation, depends on the charges. And so I just said 1 molar about. So the thermodynamic data table is quite long. We have these here. Actually, let's search for review. What is this called? Enthalpy, this is called the standard enthalpy of, not fusion, formation. Standard enthalpy of formation. Good. A lot of data tables. Here we go. We're going to go to this data table here. This is called complex ion formation constants, and then it's CD. What is CD? Let's take a look at those footnotes just to make sure we don't miss anything important. C, the ligands referred to in this table are monodentate. Chloride is called what? In our book, chloride is not, as a ligand, we don't call it chloride, we call it chlorido. Unfortunately, in the homework, they don't call it chlorido. You know what they call it in the homework? Chloro. So some people were telling me that they put in chlorido in there and they got it wrong. And then they put in chloro and they got it right. Chloro is the old system. In fact, the old system has been around for many, many years, so I still call it chloro. This, our book calls cyanido, but back in my day, I never called this cyanido. You know what I called this? Cyano. There's lots of old holdouts there, and so you'll just see it, you'll see cyano, and then you might go, what is that? Well, that's the same as cyanido. The new system, I think there's going to be resistance to it, but we'll see. Iodo, not iodido, but either, so I kind of give up, because if the homework is not following the book, then I'm not going to be very strict. So you could use either the old system or the new system. Okay. A lot of the new system I like because they made the rules easier. In the old system, they differentiated between neutral ligands and charged ligands. And then they had a numbering scheme for those, and it just got too cumbersome. So monodentate, these are all monodentate. Even though we have 4 lone pairs here, only one of them can donate. This one, what do you think it is? Cyanide. Do you think it's a carbon donor or a nitrogen donor? You can probably guess, because cyanide is extremely toxic like carbon monoxide. What do you think it is? A carbon donor or a nitrogen donor? It's a carbon donor. Cyanide and carbon monoxide are very similar. Both bind to iron 2 quite strongly, and so both quite toxic. So cyanide, so carbon monoxide, you know, you see these like suicide, you know, the cyanide pills or whatever, suicide pills. But, you know, people tried to do the same thing, but, you know, maybe they didn't have cyanide, so they hook up a hose from their exhaust pipe. Have you ever seen that? And put it into their passenger compartment. But now cars burn so clean. You know, cars don't produce much carbon monoxide. You know, not like the old days. If you have an old car, there's lots of carbon monoxide coming out of the exhaust, you know. And you got to be careful, because if you start the engine in your garage, you know, you can easily get sleepy and then eventually pass away. Nowadays it's more like CO2, you know. There's going to be a lot of CO2 coming from the exhaust, but CO2 can also be toxic, right? You know, like when you exhale, like on the space station. On the space station, the CO2 is always climbing. And if they let the CO2 climb too high in the space station, it can be very bad for health. And so what they do is they have a CO2 scrubber on the space station. They can reduce the CO2 levels. But anyway, cyanide, iodide, ammonia, or amine, you know. OH minus, what do we call that one? Hydroxido. It's hydroxide, just change the ending to O. So hydroxido or hydroxo in the old style. This one is the same, new style and old style. This one's called thiocyanate ion. Okay, so there's a question. In this case, this is linear. The carbon's going to be sp hybridized, and so this is linear. So you can only attach one end of this, either the sulfur end or the nitrogen end. You can't attach both ends because of the way it is. You know, because here the electron cloud would be pointed this way, and they're pointed in the opposite. So if you attach this end, it just doesn't quite make it. So we have thiocyanate S, you know, the hyphen, and thiocyanate hyphen N, depending on how you define. This was an interesting ligand. What is that? Have you ever heard of the 2- ligand? No, I don't. I don't know what that is, actually. Then we go to bidentate. This one is fine. Ethylene, diamine with 1 M. That's kind of a lot to write. But this is kind of weird. It's a lot to write, but if you write the name in the formula, you have to write the whole thing out. This abbreviation is used only for the formula, not the name, the formula or the structure. And so I'm going to make a note of that on the notes here. And then we have oxalate, which is oxalato. And so if this is just a neutral molecule, we just leave the name as is. If it's an ion, we change it. And so the old and the new are oxalato here. Those are bidentate. And then this one is, this is wrong. Shoot, I never noticed that. This is not, tetra means what? 4. This is the 12th edition of this book, and nobody has caught that because nobody pays attention to footnotes, right? How many people read the footnotes to these tables? And the thing is, and even our book says this, you know, as a study guide, always read the footnotes because they can yield valuable information, right? And so I usually do, but you know, something like this, I don't. To be honest, I haven't really read thoroughly everything here. And so maybe this will be fixed in the 13th edition. But it's not tetradentate. What is ethylene diamine tetraacetate? Does anybody remember? I mentioned it very briefly. And so one of the things is my memory is very bad. And so this is just, this is something I did as a student. I would always review stuff, you know, over and over. And the repetition helped me remember it. And so even if it's just straight memorizing. A lot of people look down on just memorizing stuff because it's not real learning, they say, but in another sense it is, you know, because you can build up from that. But anybody remember? I just said it for a second. It's not tetradentate, it is hexadentate. I probably went through it too fast. That's it. It's hexadentate. But even if I go through it too fast, what you should do is you should go back through and look at it. You know, when you go to conferences, scientific conferences, you know, they give like a 20-minute talk, 30-minute talk, 1 hour talk at the most, you know, and they rip through it. Like if they have PowerPoints, it's boom, 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 boom. And so they go through it so fast, I never really was able to keep up. So, but it's fine because that's standard operating procedure. I just go home and then go through it at my own pace, which is slow. My pace is, and then I try to figure out what if it was interesting. If it sounded interesting, I'd go through it slowly and try to figure out what they were talking about. If it didn't sound interesting, then good. I'm glad it was over quickly. You know, it's fast to talk. But anyway, EDTA is a hexadentate. They probably meant tetravalent. You know, tetravalent, valence is the charge. So this is tetravalent, but it's not tetradentate. Divalence is a +2 or -2, you know, whatever. All right, so when we're going to cobalt, and so we're going to just take a look at the data. Now, and the first thing is, there's some cobalt here. So we go to the cobalt here. Here, is that cobalt 2 or cobalt 3? This is cobalt 2 because EDTA is -4. -4 plus 2 gives us. This is hexadentate, so that means it has a coordination number of 6. Okay, EN is bidentate, and so what's the coordination number of this? Is this a coordination number of 3? No, it's not a coordination number of 3. Do you know what the coordination number is? 6. Because each EN is bidentate. But that means cobalt, what's the charge on cobalt? It's got to be +2 too. I'm on cobalt 3. Cobalt 3 might have a different coordination number, and so I want to look at the data to see, because this is just observation phase right now. This is oxalate, or this is abbreviation for oxalate. Well, actually, amine. Amine is what? Monodentate, but this is still cobalt +2. Oxalate's -2, and we have 3 -2, that's -6. That means that cobalt's got to be +2. This is a coordination number of 6 also. Thiocyanate. Thiocyanate is monodentate or bidentate? Or tridentate? Thiocyanate is monodentate. So this is a coordination number of 4. What's the charge? Well, thiocyanate is a -1. -1 times 4 is -4. -4, this has got to be +2. So that means cobalt +2 can either have a coordination number of 6 or 4. Maybe they're more. Did we look at enough data? Do we have enough observations to come up with a law? You know, if I stopped here, my law would have been cobalt 2 is 6 coordinate. But then I have an exception to the law, so it's no longer a law. Okay, then I don't know how they snuck in chromium, but they snuck in chromium there. But now we're here at cobalt. What is this? Cobalt 3, and it is, what's the coordination number? 6. Looks like we're okay, unless is there cobalt 3 with a coordination number of 4? Let's take a look. No, because oxalate would be, so far all the cobalt 3s have a coordination number of 6, so we're just gonna go with that. That's gonna just kind of be observational data, and that's it. Whereas, let's look at silver. You know, silver has a coordination number of 2 here. Seems like you should be able to fit more than 2 cyanides, right? But that's all they got. Or maybe silver has a coordination number of 6, or maybe a coordination number of 4, or maybe a coordination number of 2, or a coordination number of 4. Do you see a pattern? A clear pattern there? Can you come up with a law? Or do you want to come up with a hypothesis? What's going to be your hypothesis? Why is the max here 2 when the max there is 6 and the max there is 4? Why do we stop at 2 with cyanide? Why don't we go full attack and get 6 cyanides on there? It doesn't happen. And so these are all the things you have to incorporate into your hypothesis, because the hypothesis is going to be a fundamental description. And then you take your hypothesis and then you try to convince everybody to agree on your hypothesis. And when everybody else agrees on your hypothesis, then you're going to call it the what? Theory. So this is why I say just look it up, and then when we look it up, we're going to say, okay, it's 6. So how many more ethylene diamines can I attach to this? So far I have a coordination number of 2. How many more ethylene diamines can I attach to this? 2 more. And so what's that going to look like? So let's go ahead and do that here. And I think I accidentally dropped this. Might have died. I have a new one that's coming, which I'll bring next time. Give me a moment. Let me try this one more time. That's not working. So I'm going to do plus 2 more ethylene diamines, EN for short. And then what I'm going to do is draw this. So now it's going to have a coordination number of 6. The coordination number of 6 adopts an octahedral geometry. And we need to put these, link them together. So I'm going to do this shorthand rather than the long method like this. I'll just do an EN like this, and then maybe another EN. These are going to be adjacent sites in the octahedron, and then an EN like this. So there we would have it. Now the charge is going to stay at 3+, and this whole thing is going to be 3+ charge. And so let's name this. So naming this, how would I name this? Oh, maybe it's working now. Yeah, now it's working. So I'm going to go back to this here. So you could either write it all out, you know, or you could use the abbreviations. There are different ways you could write it out. You can condense the hydrogens in there so you don't have to draw out the bonds for the hydrogen. Like that. That's another way. Or you could write like this, a nitrogen and a nitrogen, and then an EN like this. Or you could just write it like this, not even show the nitrogen, just say EN. So there are different ways you can write this out to save yourself some drawing. And so these are different ways of drawing the ethylene diamine you'd be familiar with. But we need to name that. And so when we write the formula is always written with the metal first, and then the ligands. And we have 3 ethylene diamine ligands, and then we write the net charge. The net charge is the cobalt's +3, the ligands are 0, so this whole thing carries a net charge of 3+. Now, the formula is written with the metal first, but the name, the formula, metal first. The name has ligands first. So formula, metal first. Name has the ligands first. And so when I name this here, I'm going to name it, well, if I have to name the ligands are ethylene diamine, and how many of those do I have? I have 3 of them, so I'm going to call it triethylene diamine. That would be the name of the ligands. So, but this leads to confusion. Can you see where the confusion is going to come? The confusion is going to come here. This appears as if I have 3 ethylenes, the CH2, CH2, so I have 3 of those, and 2 of the means, the NH2s. The means need not be NH2s, they could just be nitrogen. Could be with carbons as well. And so what we have is we have a separate numbering system, because we don't want this to sound like I have 3 ethylenes. I want it to sound like I have 3 ethylene diamines. So instead, we call it tris. And so this is going to be tris ethylene diamine. And then we could leave it like that. Or we could be even more emphatic by putting the ethylene diamines in parentheses. And so this clearly would be 3 ethylene diamines. All right, once we do the ligand name, then we just add the metal to the end of this. But we have 2 ways of naming the metal. One way of naming the metal is if the complex is positively charged or neutral. If the complex is positively charged or neutral, we leave the metal the same. However, if the complex has a negative charge, as an anion complex, we change the metal to the 8 ending. That is, we just add the 8 suffix to it. And so this, we have 2 choices for the metal, cobalt or cobaltate. Which one would we call it? Cobalt or cobaltate? We call it cobalt. We call it cobalt because it's the positive or neutral. And then we add the charge, not the net charge here. The Roman numeral 3 refers to the charge on the cobalt, not the charge on the complex. And so this would be called trisethylene diamine cobalt 3, all one word. Ion. Ion would be a separate word. Okay,
Just a quick question, clean it up, but the cobalt ligands are both in the parentheses there and it's not. Just because you have it with the parentheses, so I want to make sure that you write cobalt 3 with both of the 2 ways you wrote tris ethylene diamine.
yeah, here.
Okay, great.
Yeah. It would be here too. This parentheses is not really necessary. Okay. And so you could just use the first name, trisethylene diamine cobalt 3, Roman numeral. Ion. You don't need the word ion because you could figure out it's an ion just based on adding up the charges. So some people are sticklers for that. I'm not. Okay, let's take a look at some other examples of naming. these. The more examples, the better. So I'm going to kind of go through these quickly, but we can go through some of them slower. Like, what happened to my table? I'm lost in my data table. Okay, this is the thermodynamic. Table of isotopes. All right, back. I tried to blow it up, but it threw me to a different page. All right, so here, we're gonna just use a standard. The only time we use actually, let me write the other ones. We have bis is 2, tris is 3. The only time we use bis and tris are for ethylene diamine kind of thing, or any ligand that has one of the other numbering schemes in it, that is di-tri. But this would be what? Cyano or cyanido, I don't care, one of those. I like dicyano. Dicyano, silver or silverate. Well, silverate doesn't sound so good. What sounds better than silverate? Argentate. So this is going to be dicyano, silver or argentate. Well, which one we use depends on the net charge. The net charge is negative. And so since the net charge is negative, we use the other naming system, and we're going to call that dicyano argentate, and the charge on silver is, well, cyanide is -1. You have two of those, -2 plus 1. It's going to be +1, gives us some net charge. So it's going to be Roman numeral 1. Now silver is a fixed charge. The only charge on silver is +1. But, and we never use a Roman numeral when we're talking about silver nitrate. We don't call it silver 1 nitrate, we just call it silver nitrate because there's only one charge on the silver ion. But here we use a Roman numeral for everything. And so you would never use a Roman numeral 1 for silver in the normal nomenclature scheme, except for these. Okay. All right, how about this one? Now, this is the abbreviation. EDTA is so long, but we need to know how to name it. Do you know how to name this? Let me show you what EDTA looks like first. Actually, I don't even want to go back. Yeah. EDTA is this. We probably can figure it out. I'll just show you what it is. Unless, are we out of time? 1 minute. All right. The first part, the E stands for ethylene. What does the ethylene look like? Two carbons. And so it would be ethylene. The first part stands for ethylene. CH2, CH2. That's the E. Diamine. Okay, NH2, except it doesn't have to have 2 hydrogens. It's just an amine. It could be hydrogen or carbon. In this case, it's going to have no hydrogens. And then tetraacetate. You know what acetate is? Acetate, okay, so what we're going to do is we're going to throw in an acetate here. And the acetate is normally CH3COOH. But we're going to make this a CH2COOH. CH2COOH. Oh, that's not acetate, that's acetic acid. I'm going to make this acetate. I need to get rid of the hydrogens and replace those with a charge. And so this is going to be minus. This is going to be minus. And then we're going to have CH2, COO minus, and CH2 COO minus. And then there's going to be a lone pair on the nitrogen. This is still an amine, but it doesn't have any hydrogens. And this is still an amine because it's going to behave like ammonia. There's a lone pair, that lone pair is going to be a donor, except now we have 3 carbons bonded to it. This in organic chemistry, they call it a tertiary amine. A primary amine in organic chemistry has all hydrogens. A secondary amine in organic chemistry has 2 hydrogens and 1 carbon. In tertiary, did I get it right? A secondary amine has 2 carbons, a tertiary amine has 3 carbons. And so they have fancy names for this. Uh-huh.
So the T is for tetraacetate.
Yeah, this would be tetraacetate. And so ethylene, diamine, tetraacetate. It's easy to remember. Even though it's a big formula, it's easy to remember if you know what the parts mean. Anyway, I'll stop here. We're almost done with this chapter. Again, the homework, the due date, ignore the due date on the homework. I'll fix it when I get access to Mastering Chem again, which will hopefully be before the end of the semester.